NEC Section 250.30 addresses the grounding requirements for separately derived systems. This section mandates that a grounding connection should not be established to any grounded circuit conductor on the load side of the point of grounding within a separately derived system. An exception to this rule is specifically permitted within the same article. The exception to this rule is found in Section 250.30a on. This particular subsection dictates that a grounding connection must be made to the grounded circuit conductor of a separately derived system. This connection is to be made either at the service disconnecting means or at the source of the separately derived system, particularly if there is no service disconnecting means present. To elaborate further, a separately derived system refers to an electrical power source such as a generator, transformer, or converter that derives its power independently from another electrical system. It's crucial to ensure proper grounding of these systems to maintain electrical safety and prevent potential hazards. Grounding provides a low impedance path for fault currents, enabling overcurrent protection devices like circuit breakers or fuses to quickly interrupt the circuit in the event of a fault. This process minimizes the risk of electrical shock, equipment damage, and fire. Section 250.30 of the National Electrical Code emphasizes the importance of establishing a single point of grounding for separately derived systems. This single point is intended to prevent the circulation of objectionable ground currents, which can lead to voltage drops, electromagnetic interference, and inaccurate readings from sensitive electronic equipment. The general rule outlined in Section 250.30 prohibits grounding the neutral conductor on the load side of the separately derived system. This is to avoid creating multiple ground paths, which can cause ground loops and increase the risk of circulating ground currents. However, Section 250.30a provides an exception to this rule, allowing the neutral conductor to be grounded at the service disconnecting means or at the source of the separately derived system, especially when there is no service disconnecting means. The service disconnecting means is essentially the main switch or circuit breaker that disconnects the entire building or facility from the utility power supply. In the absence of a service disconnecting means, the grounding connection must be made directly at the source of the separately derived system. This source could be a generator, transformer, or other power conversion device. The purpose of grounding the neutral conductor at this point is to establish a reference point for the system voltage and to provide a low impedance path for fault currents to return to the source. This grounding connection should be made to a grounding electrode system, which typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes that are in direct contact with the earth for at least 10 feet. The grounding electrode system must be effectively bonded together to form a low impedance path to ground. This bonding ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of electrical shock. In addition to grounding the neutral conductor, it is also essential to ground the equipment grounding conductors of the separately derived system. Equipment grounding conductors are the wires that connect the metal enclosures of electrical equipment to the grounding electrode system. These conductors provide a path for fault currents to flow back to the source in the event of a ground fault, tripping the overcurrent protection device and energizing the circuit. The equipment grounding conductors must be sized appropriately to handle the available fault current. The size of the equipment grounding conductor is determined by the size of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. Furthermore, it is important to maintain the integrity of the grounding system throughout the installation. All grounding connections must be made using approved methods and materials, such as listed grounding connectors and clamps. The connections should be clean, tight, and free from corrosion to ensure a reliable electrical connection. Regular inspections and maintenance of the grounding system are also essential to identify and correct any potential problems. This includes checking the tightness of connections, inspecting for corrosion, and testing the grounding electrode resistance. The grounding electrode resistance should be low enough to provide an effective path for fault currents to flow to ground. The NEC recommends a grounding electrode resistance of 25 ohms or less. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. It's important to note that the specific requirements for grounding separately derived systems can vary depending on the voltage, size, and application of the system. Therefore, it is always essential to consult the latest edition of the National Electrical Code and to seek guidance from a qualified electrical professional to ensure compliance with all applicable regulations. In summary, NEC Section 250.30 and its exception in Section 250.30A provide the guidelines for grounding separately derived systems. By adhering to these requirements, one can minimize the risk of electrical shock, equipment damage, and fire, creating a safer electrical environment. Proper grounding is not merely a code requirement, it is a fundamental safety practice that protects people and property. Therefore, it should always be given the utmost attention during the design, installation, and maintenance of electrical systems. Let's consider a practical example to illustrate the application of NEC Section 250.30 and its exception. Imagine a building with a standby generator that serves as a separately derived system. The generator provides power to essential loads during a utility power outage. In this scenario, the generator's neutral conductor must be grounded at the generator itself, which acts as the source of the separately derived system. This grounding connection should be made to a grounding electrode system, such as a ground rod or a connection to the building's metal water pipe, provided that the water pipe is in direct contact with the earth for at least 10 feet. Additionally, the equipment grounding conductors of the generator and the equipment it supplies must be connected to the same grounding electrode system. This ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of electrical shock. Now, let's consider a scenario where a separately derived system is supplied by a transformer. In this case, the neutral conductor of the transformer's secondary winding must be grounded at the transformer location. This grounding connection should be made to a grounding electrode system similar to the generator example. The equipment grounding conductors of the transformer and the equipment it supplies must also be connected to the same grounding electrode system. It is crucial to ensure that the grounding connections are properly sized and installed according to the NEC requirements. The size of the grounding conductors must be adequate to handle the available fault current, and the connections must be clean, tight, and free from corrosion. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking the tightness of connections, inspecting for corrosion, and testing the grounding electrode resistance. In addition to the specific requirements for grounding separately derived systems, it is also important to follow the general grounding requirements outlined in the NEC. This includes bonding all metallic parts of the electrical system together, such as metal conduits, enclosures, and equipment frames. Bonding ensures that all metallic parts are at the same potential, minimizing the risk of electrical shock. The NEC also requires the use of ground fault circuit interrupters, or GFCIs, in certain locations, such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to detect ground faults and quickly interrupt the circuit, preventing electrical shock. In summary, grounding separately derived systems is a critical aspect of electrical safety. By adhering to the requirements of NEC Section 250.30 and its exception, along with the general grounding requirements of the NEC, electrical professionals can ensure the safety of people and property. Always remember to consult the latest edition of the NEC and to seek guidance from a qualified electrical professional when working with electrical systems. Understanding the principles of grounding and bonding is essential for anyone involved in the design, installation, or maintenance of electrical systems. It is a fundamental aspect of electrical safety that should never be overlooked. This explanation of NEC Section 250.30 and its exception provides a solid foundation for understanding the requirements for grounding separately derived systems. By applying these principles in practice, one can ensure the safety and reliability of electrical installations. Furthermore, it is beneficial to delve deeper into the specific requirements for grounding electrode systems. The NEC provides detailed guidelines on the types of grounding electrodes that are permitted, the methods for installing them, and the requirements for bonding them together. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. Ground rods are typically driven into the earth to a depth of at least 8 feet. Ground plates are buried in the earth at a depth of at least 30 inches. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. When using metal water pipes as grounding electrodes, it is important to ensure that they are electrically continuous and that they are not insulated by paint or other coatings. The NEC also requires the use of a supplemental grounding electrode when using a metal water pipe as a grounding electrode. This supplemental electrode can be a ground rod or a ground plate. The purpose of the supplemental electrode is to provide an additional path for fault currents to flow to ground in case the water pipe becomes disconnected or corroded. All grounding electrodes must be bonded together to form a low impedance path to ground. This bonding is typically accomplished using copper conductors or bonding jumpers. The size of the bonding conductors must be adequate to handle the available fault current. The NEC provides guidelines on the size of bonding conductors based on the size of the service entrance conductors. In addition to bonding the grounding electrodes together, it is also important to bond all metallic parts of the electrical system together. This includes metal conduits, enclosures, and equipment frames. Bonding ensures that all metallic parts are at the same potential, minimizing the risk of electrical shock. The NEC also requires the use of equipotential bonding in certain locations, such as swimming pools and agricultural buildings. Equipotential bonding involves connecting all metallic parts in the area to a common bonding grid, creating a zone of equal potential. This reduces the risk of electrical shock by minimizing the voltage differences between different metallic surfaces. In summary, grounding electrode systems are a critical component of electrical safety. By understanding the requirements for grounding electrodes and bonding, electrical professionals can ensure the safety and reliability of electrical installations. Always remember to consult the latest edition of the NEC and to seek guidance from a qualified electrical professional when working with electrical systems.